So tonight we're going to hear from Ian Bushfield, who a lot of you probably already know. He's the Executive Director of the BC Humanists Association and also works with the Cerebral Palsy Association of BC. But tonight we're going to talk about your master's work, weighing paper with lasers.
Yeah. Thanks, Susan. As she said, my name's Ian Bushfield. I did a master's in physics at SFU, and that's mostly what I'm going to talk about tonight. It was in a lab of terahertz research. So I'm going to talk about terahertz, which is a far infrared band of the electromagnetic spectrum that's fairly interesting. Before Simon Fraser, I lived in Edmonton, and I went to the University of Alberta, and there I did an engineering physics degree where I spent 3 summers and my senior project in a different terahertz lab. Actually, so I do know, in theory, something about this topic that I haven't forgotten in the last year or two since I've been out of physics. When I first moved to Vancouver and started at SFU, I actually went into a Bose-Einstein condensation lab in physics because it's a really cool, fascinating kind of matter, state of matter that only exists at really cold temperatures. But it turns out quantum mechanics is really hard, and I didn't want to do quantum mechanics. I wanted to just play with the lasers, and this is exactly what I got to do. So that's what I'll talk about tonight. My project was funded by the NSERC's Industrial Postgraduate Research Scholarship. For all the talk you've probably heard, the federal government is really shifting from the pure science towards the applied industrial science. And for the most part, we don't like that, I think, as sort of the science skeptic-minded researchers should do what they want. But for me, this actually worked out because I ended up getting a scholarship where it was partially funded by the federal government, partially funded by my university, and partially funded by a private industry, Honeywell Corporation. I heard that Honeywell could offer me money, and I was like, well, I don't want to work in the cluster bomb section of Honeywell. And luckily I didn't, so I was safe there. So my project was on weighing paper with lasers. Honeywell's facility here in they have a facility here in North Vancouver that you probably didn't know about, located on Brooksbank Avenue by the big MEC, Mountain Equipment Co-op. And so I spent a couple months there and commuting back and forth between SFU doing research at the 2 different labs. And their big question is, how can we develop a better sensor for paper production? Because they have a big pulp mill down outside of Portland where they're always trying to find better ways to make paper cheaper. So just normal like copy paper or newspaper, like actual paper. And so the sensors sort of sit in this very near the end of the production line and sort of just keep track of what's going in, because paper is just water, air, and wood. And if you get the mixtures right, you can sell people a lot of water, which is cheap, and less wood, which is expensive, but still have a decent product. So what is terahertz radiation? We've all hopefully seen the electromagnetic spectrum in one form or the other. Terahertz means 10 to the 12 hertz. Well, the frequency that corresponds to is less than light and more than radio waves. This was commonly known as the terahertz gap up until about the 90s, and most papers written about this radiation still sort of talk about the terahertz gap, even though it's been filled in by research in the last 20 years. Why there wasn't a lot of research into this before the 1980s it was just a technological issue. On the lower end here, we have radio waves and microwaves. These are things we can do with electronics, so we can develop a circuit that just resonates fast enough to generate radio waves and generate an accelerator in your microwave. And then at the higher end, we can use light bulbs and traditional lasers to fill in basically everything up here, and then some more atomic effects to do the higher ones. But there was this little gap in sort of the half a terahertz to about 100 terahertz range where there was no radiation being produced, or we couldn't produce this radiation in very discrete wavelengths. But there was some cool physics there. This area is of useful information because it's very strongly absorbed by water, but not much else. So it will go through cloth, it will go through plastic, but it'll reflect off metal, or it'll pick up, but you can measure water and other radiations. And so we want to explore this area because scientists are like that and they just want to test everything. So we started figuring out ways to get radiation out of that, and I'll talk about that in a minute. But first I'll show you what's really interesting about the sort of terahertz radiation we worked with is that the measurement technique gives you the electric field. So hopefully you remember from high school physics that light is an electromagnetic wave. It comes as generally, vibrations of electricity and magnetism. Well, terahertz radiation, you can measure the electric field of it directly. So rather than just measuring the intensity or the amplitude of it, you get the actual positive and negatives here, which means you can get a full frequency spectrum and also the imaginary part that this matters. The type we generated also only made a single cycle. So most waves you think about oscillate continuously. This one just oscillates once. You get a nice big pulse. And that pulse you can use to kick materials. And when you kick materials, you can see how they respond. So the whole sort of field of terahertz radiation is about throwing kicking a material at a certain frequency and just seeing what happens to it. That's basically it. And these are pulses I actually took. Right here is 50 separate pulses overlapped. Because we use lasers, they repeat on a regular cycle, which means we can get a lot of data really fast. And so I can take 50 scans, and they overlap almost perfectly. And you can see in the frequency domain, they also overlap, and we get a bandwidth from about 100 gigahertz to a terahertz. Other systems can get much broader ones, up to 5 or 10 terahertz. And our signal to noise here is actually pretty crappy. So this is actually a pretty noisy system, and that's why some of my results weren't as good as I'd hoped. But there's a multitude of reasons for that. So this is what the basic experiment looks like, and I'll show you what it actually looks like on the table in a second. But here's the schematic picture you should keep in your mind. So we have an ultra-fast laser, and I'll talk about that and show pictures of it because it's really cool. We have an ultra-fast laser, and we split the beam in two because we need one beam to generate a terahertz pulse, and we need one to detect it. As soon as we take one beam to generate it at the emitter stage, and then the blue lines here are our terahertz pulse. We send that through our sample, and then eventually focus it on our detector. And the trick to this technique is that each pulse out of the laser down here meets at the detector at the same time. But we can adjust this delay stage to shift the pulse and sort of trace out our terahertz wave. This will make more sense as I show you what the laser does. So this is our laser. This was the laser I used in Edmonton, and it's just cool to look at because you can see it, right? There's a beam there. But that's not actually the beam that's powerful. So the way this laser works is right over here, there's a really powerful diode laser, basically a laser pointer on steroids. That laser runs into this other laser. Basically, our Edmonton lab had 4 lasers. The one in Vancouver I used was only 2, but we could also go up to 4. And they actually got a grant to expand the Edmonton lab, and I think they have one that has 6 lasers. So they have a laser that powers a laser, that feeds another laser that's powered by another laser, and then that process can repeat. So this is basically just so you can get really powerful pulses to do cool things, because most of this relies on sending light that's so powerful it messes up matter, so it behaves differently than we normally expect. So our diode laser goes into this crystal here and oscillates back and forth. So this box here, the only part that is actually lasing is the little crystal in the middle. That crystal is called titanium sapphire crystal, and it generates laser in 800 nanometer wavelength. So this red here is about 700 nanometers, so it's really dark red thing. You can just barely see this. You usually need, it's on the edge of our eyesight. And the way this works is there's a long cavity, so the pulse goes through the crystal, bounces back and forth, and every time it goes through that crystal, it picks up a little more power from the diode laser. But it's pulsed. It doesn't have to be. So most lasers come out in a continuous stream. What happens in this laser cavity here is you have the 2 mirrors, so you can set up standing waves. And one thing you might remember about waves is you can set them up so they add and together. It's called superposition of waves. And so you can get a bunch of different standing waves in this cavity, and if you hit it, and you actually literally hit one of the mirrors, you shake it, and it causes something called mode locking, and then all of these standing wave overlap, and you get a pulse that is about 10 femtoseconds long. So a femtosecond if you remember your units, is 1,000,000 times less than a nanosecond. So it's 10 to the minus 15 seconds. So we get these ultra short pulses coming out of this laser. And the motto of our Edmonton lab was light moves slow in the lab, because to travel a foot, light takes a nanosecond, or to travel 30 centimeters, it takes a nanosecond. So if we can measure 1,000,000 times more accurate, that means we can measure, you know, 1,000,000th of a foot in with light pulses, and that's how small our light pulses are. So that beam, after it comes out of that laser over there, goes through some stages and comes into this bigger one, and this is also our Edmonton lab because I didn't take good pictures of the Vancouver lab. Goes through this bigger laser, and it's powered by this really big gas laser, which comes through a beam because if it was, or it comes through a beam tube because if you stuck your hand in there, it would burn, and is powered in the same way through this crystal. So there's another oscillating path in there to help build really big, powerful pulse. So then we take those pulses and we fire them like I showed you that previous cartoon picture. Here's the actual lab bench setup, and again, this is the Edmonton lab, but we had a very similar setup here in Vancouver. And you fire it at the emitter, or the terahertz crystal. So you have a little crystal or an antenna, and I'll show you the different ways we can generate terahertz pulses in a second here, and then you just propagate the terahertz pulse through air. And I told you before, it does absorb a little bit of water, so as you go through air, it tends to degrade your signal. So what we tended to do was put it in a nitrogen chamber where we could get all of the water vapor out. And what we actually had in Edmonton was we had a vacuum chamber where we could suck all the air out and get a perfect signal coming through it. But anyway, so our terahertz signal goes through and is met with a detector signal and measured on some electronics that let us do all the fancy signal detection. And we can set our sample wherever we want, if we want it at a focus or if we want it sort of in a parallel spot. So how we generate these pulses, there's two main ways. This one way is with crystals, and these ones are zinc telluride crystals, or special manufactured crystals that we can get, where when you put that high-powered red laser beam that we made with the lasers I showed you, it goes nonlinear. So generally when light goes through a material, it behaves normally. You know, it refracts a little and bends or slows down and then comes out the other side. But if you put a lot of light through, it messes around with all the materials in the crystal and starts to interact with itself. So, depending on the crystal, it will interact in different ways. And there's a lot of math that can explain how each of this happens. But in this crystal, it undergoes a first-order nonlinear process, which means sort of the first screw up it can do to the crystal, called optical rectification. What that means is the intensity of the laser pulse is inducing polarizations in the crystal. So think of the crystal as little crystals inside of it, and as the pulse goes through, each of those crystals is being polarized. So one side goes positive, one side goes negative, and as those flip around, it creates, as charges accelerate, hopefully you'll remember they create electric light. They create light, or they accelerate electromagnetic waves. So that's sort of what happens in here, but not exactly. What we use here in Vancouver, you can use a lower powered beam, and it's called a photoconductive antenna. So this is just a semiconductor wafer. We tended to use gallium arsenide, but you could use other kinds like silicon if you had the right laser. And the idea is you put a huge bias voltage across these two wires. So on top of your wafer or semiconductor, you had just patterned little metal wires. And you can do this in a big way too. And then when your laser beam hits it, it excites electrons. So they're sitting in the conduction. So the way a semiconductor works is if you put voltage across it, no current will flow. But when you hit it with light, you can actually excite electrons that can then move around in it. So if you have a voltage across here, and then you hit it with a light pulse that's strong enough, you excite electrons that then accelerate from one side to the other. So as the electrons accelerate when the light pulse hits, that creates our terahertz pulse, because accelerating charges create electromagnetic radiation. Very complicated physics, but it happens to all work. And the way you detect terahertz is in the exact opposite way. You hit a terahertz pulse here, it shakes electrons around, when they're excited, and then you just measure that current. It's a little trickier here, but it goes in kind of the reverse. So coming back to my thesis, we wanted to know, how can we measure paper with this? I mentioned earlier that paper is made up of water, wood, and air on a simple model. And we know already that terahertz is strongly absorbed by water. And we can start to think about, if we can tell there's a difference between air and wood, we can break paper into 3 components that sort of fit into one medium and create a model of that. So my goal was to create this model of the absorption and index of refraction of the paper, so that when terahertz radiation went through it, we could see the change in the pulse and predict it. Basically figure out how the pulse changed to figure out what it hit, so how much water, fiber, and air was in that paper. And then the ultimate idea would be you'd stick that sensor, that little terahertz pulse right here, and send it back and forth as the paper flowed through. And if you measured an increase in water, you could then just turn the dial down earlier with the control system. And it turns out you can also get terahertz systems that are much smaller than the ones I just showed you. You can get a fiber optic box that fits on a tabletop, so you don't need a huge lab to do this. So it does make sense. And the point of it would then be, if we can get 3 components per paper, we can then make 3 different measurements. We can measure its mass or its density, we can measure its thickness, and we can measure the water content, how much water is in there. And if we can measure 3 things at one time with a contact laser-based sensor, we can take other sensors out. One big issue in paper manufacturing is, you'll notice they have these giant sheets. Now there's no scale on here, but they assured me that these are about the width of a football field at times. And so if you have a sensor that's telling the thickness by pinching it, and there's a little catch, I just have the cartoon picture of paper flying everywhere. And so you want sensors that don't touch the paper, but still give you the same accuracy as something that pinches it, or other ways. And they do have other sensors, like based on other lasers, but nothing that's really combined the 3. To measure the weight, they actually often use nuclear radiation fired through it. So some of your paper might be a little radioactive. So when you actually do the experiment, this is what you sort of look at and stare at for a while, and then let computers figure out what actually happened. But I won't bore you with that part. I'll bore you with the picture graphs. So here's the reference pulse that just goes through air. And then if we send it through a really thick piece of pulp paper that's 1.5 millimeters thick, you get a change in the pulse. So it goes from this to that, basically. And the point is that if it's a thick piece of paper, paper will take longer to go through than air because it has a higher index of refraction. Light slows down in thick stuff. So we can tell that it's already shifted, and it's shrunk, so it's been absorbed by some of the paper, so some of the water in the paper is absorbed it. And then if we compare, say, an 800 micron and a 1500 micron piece of pulp paper, we can see there's a little change in that graph as well. So we can start to look just qualitatively even until there's a difference in the amount of water in those 2, just because a thicker piece of paper will have more water in it, right? And it will also slow it down more. So those are the kind of qualitative ways you can start to look at it. Once you build the model that I won't actually get into unless you really want me to, because it's a lot of math, and I have it in later slides, but I won't show it. You can get graphs that look like this, that don't necessarily mean anything. So this is showing you what the 3 components I talked about, water, fiber, and air, and how they break up. So I took a bunch of different samples, about 12, and just basically compressed them to get different densities and thicknesses, and they all have about the same moisture content. And the the lines here are what they should be, what the predictions would be. And then the data points are sort of where my measurements came out. So you notice they're not bad up here. There's no error bars because my lab doesn't do that. And then down here, there's some issue with the water going really far off. If I convert it to the standard units of the paper manufacturing of thickness, basis weight of grams per square meter, and moisture content percentage, the graphs just don't. They're in the right ballpark, but they don't look that good. They don't look as good as the simulations I did. And part of that comes down to subtleties in the model that I hadn't quite worked out yet, and a very low signal to noise. So our laser was very noisy. when I was taking my measurements. And the grad student who continued this work on, I think they were telling me he made orders of magnitude improvements in just a week, of course. So it was just me. So that's sort of where my results came to. Now, I mentioned there was other ways to get paper, and I teased online that other possible techniques of terahertz can involve porno scanners, alcohol, and death rays. So the first one I'll talk about is the full body scanners. If you've been to the Vancouver airport, you've probably seen the giant TeraView, and if you've been lucky enough, they've made you like stand there and do the position while the machine buzzes and whirs around you. Now there's two ways those machines can work. One is with backscatter X-rays, which scares everyone because X-rays are ionizing radiation. The other is with terahertz radiation. The terahertz ones, as I mentioned, go straight through cloth and paper, or cloth and plastics, but they'll bounce off water. So because our bodies are 70–80% water, you can effectively make, the X-ray glasses that kids always wanted to look through other people's clothes, and you generate pictures like this. So because terahertz has a wavelength of about 300 microns, you can get very high resolution images. Now I don't know if they actually did this with a scanner or if this is just sort of their idealized version, but it gives you the idea. So the idea of the scanner at the airport would be it bounces off the metal of the gun, the knife, and the other gun, but it goes straight through the clothes he's wearing. And you notice there's some slight absorption in whatever he's got in his shoulder. So that's how those scanners work, is they fire the terahertz submillimeter ray at you, it bounces off you, and then they just detect it. The way backscatter X-rays, they do the same but with X-rays, and they're supposedly softer, low-power X-rays. The advantage of using terahertz or submillimeter is because it's far infrared radiation, it can't ionize you, molecules in you. It can't really cause any health effects. And the amount of power they're using to take these images isn't high enough to really worry you. The next data I'll talk about is a really interesting lab that's in Denmark. I would always read about their papers and their studies, and they did fun stuff with terahertz radiation. So this graph here is showing alcohol content versus estimated strength. So they developed a model whereby you could detect the amount of alcohol in a fluid or in a mixture based on its terahertz absorption properties. And so they did that, and they mixed water and alcohol in different percentages from 0 to 100 and plotted it. And I said, that's boring. So they went to the liquor store and bought everything they could find, and that's what these blue stars are. They don't tell you which ones are which. But you notice that little guy. Anyone have a guess of what that little guy is from the liqueurs you could get?
So
about 16%.
Almost 40?
Alcohol. No, sorry, that little guy has a 16% actual alcohol strength.
But it's advertised as 40?
No, this is what the terahertz system is telling.
So what's the difference between
Sure.
actual and...
So this is what the label says,
Oh, okay.
and this is what their system told them, what their laser said.
Sherry?
Stronger?
No, it's actually Bailey's, because the milk content of it screwed the whole system up. So the idea of this system
That's a trick question.
was that they could,
Oh, it's good.
the way they advertised this experiment, probably to get more funding, because a lot of funding for this research is coming from defense and security agencies, was, well, if we know how much alcohol is, we can sort of detect whether it's flammable. So this is a bomb sensor, and we can tell if that water bottle you're carrying is dangerous or not. And what was really cool about this experiment was they were actually able to do the test through a glass. So they fired the terahertz pulse at a glass. One beam would reflect off the glass on the outside, and that would be their reference. That would tell them what the pulse should look like. The other would bounce off the inside between the glass and the liquid and bounce, and that would tell them what the fluid was. So they could compare those two pulses and get this graph. They also did some work in Denmark there about looking through shoes for explosives and similar things. So they
Could you do that on a blood sample?
could you do that on a what, sir?
Blood sample?
Blood sample?
Yeah. Instead of a breathalyzer.
The issue with blood, I believe, would be the high sugar content and the high iron content. Because every different mixture has different stuff in it, it's going to react differently. So They expanded their model a little bit and also measured sugar levels. So they tried to measure simultaneously sugar and alcohol content, and in the same paper, and they did it reasonably effectively, but they didn't have as pretty of a graph that just had this nice straight line.
But in principle,
I hadn't seen anything with blood though.
in principle, refining this though, if you could figure out what the properties of the baseline for blood was, you might be able to actually.
Yeah, the trick is finding whether or not your material reacts in this frequency range, and that's why, this works really well for stuff that has water, or stuff that's very similar to water.
What was the component in Bailey's that made it responsive?
I think it was the milk,
What
the
part of
lactose
milk?
probably.
Lactose? Oh,
Maybe,
it's
I'm
more,
not
more
sure.
the sugars than the fats or the proteins.
I'm not sure actually,
Okay.
but I definitely know it was Bailey's that was off.
Yeah, that is a sweet one.
And so the final, oh sorry,
Would it work? Would it need to be in a liquid?
sorry?
Could you do it in vapor, say? Or?
Vapor would be tough. You could use a lot of vapor or a dense vapor, just because it's low reactivity.
Yeah.
You could do in powdered and solid form.
I was
if you
just thinking about that
put it on a
alcohol
sheet.
example, thinking about like a breath.
Oh, breathalyzer? I don't think it'd be strong enough. You'd have too much water absorption through the air. So the final one I found is someone did write a paper called terahertz death ray. If you read the abstract in the paper, it's actually just a really powerful terahertz beam they made at 10 megawatt per centimeter squared, and it doesn't talk about biological effects or anything. I think they just wanted to see if a conference would accept terahertz death ray. So I promised you a death ray and I gave you one. That's my quick run through. This is Steve Dodge, who sponsored me at SFU after I quit working on Bose-Einstein condensates. This is the facility in North Vancouver that Honeywell helped me fund. Thank you.